Okay, I don't know what this thing is, but it has been on my screen for a lot of time now. This weird dent. Anyway, just ignore that. Let's do it. Okay, the first question. So it's on A, right? Okay. F is equal to this thing, continuous at x equal to 3, then lambda is. So x plus 3, whatever, just put 3 in there. 3 plus lambda is equal to 4 is equal to what when you put 3 in there? It's like also at x bigger than 3, so it's just 9 minus 5, which is 4 as well, so that just means lambda equal to 1, so it's D. Next question. Second is what, if this is continuous at x equal to 0, then the value of k is, okay, so x square sine square of, okay, sine of 1. Look, this thing approaches some weird value, right? It's in between -1 and 1, right? We don't care about what the value is, it's finite, and then x square times that is 0, right? So k should be 0. Yes, it's C. Third is if f of x is equal to this thing, and it's continuous at x equal to 1, then the value of k is, okay, so come on, just polynomials one second, like fine, just it is what, 3, I guess, yeah, so k should be 3. So C. Next question. Fourth, the value of k for, okay, which makes f of x is equal to this thing, continuous at x equal to 0 is, so at x equal to 0 is just k, and this thing is fine, so x equal to 0, this thing, oh wait, there's no values that this could be happening, because sine of 1 upon x, that's oscillating wildly, and cosine x is 1, right, at x equal to 0, which means this thing, right, it's actually like, yeah, it doesn't, it's gonna oscillate so much, right, that it doesn't have a single value that it goes to, right, there's no limit for this thing, which means there's no such value. Okay, it can never be continuous. The value of m for which the function is continuous at x equal to 1 is, for which this function is continuous at x equal to 1, right? So it's 2 is equal to what? Equal to m. Come on, seriously, give me something better than these plug in the value, get the value kind of questions. Okay, if this function is considered x equal to 0, then the value of k should be, seriously, so at x equal to 0, okay, at x approaches 0, what is this thing going to be? It's like 1 power, yeah, I get it, it's just, so cosine x power 1 upon x, right? It's like 1 1 plus cosine x minus 1, or I should say something like this thing, 1 minus cosine x, maybe not, so like 1 plus cosine x minus 1, whatever this thing is, positive or negative, it's approaching 0. That's what you should be thinking about. So then this power, what, 1 upon cosine x minus 1, this will approach e, but then you want this to the power of cosine x minus 1 upon x, right? So that is still going to be the same quantity. And then this thing just approaches e power cosine x minus 1 upon x, which is e power negative. So 1 minus cosine x upon x, that just becomes 1 upon 2, right? As x tends to 0. So it's e power negative 1 upon 2. That's what k should be, which is not here. What is going on? Why is that not here? That should have worked. Yeah, I mean, k should be e power negative. Why is e power negative 1 upon 2 not here? There's e, there's 0, there's, but why not e power negative 1 upon 2? Now, this is just wrong. This is just wrong. We did the math. We know it has to be e power negative 1 upon 2. There's no other way. Okay, seventh. Seventh is if the function, this function is continuous, right? It's continuous in the interval 0 to pi, the number of ordered pairs a to b is. So x squared plus a squared sine x, that's continuous, of course. But then, so like 0, not a big deal. Pi upon 4, at that point, it's changing definitions. This is, okay, all these functions are like continuous when they're all over the real numbers, but they are now in intervals. So pi upon 4, just put that in there. Pi upon 4 plus a square square root of 2, and then sine of x is just 1 upon square root of 2. So it's a square. That's going to be equal to, when you put pi upon 4, it's just b plus, what's this thing? So square root of 2 pi upon 4 cosine of x is just 1 upon square root of 2. So like, it's just, yeah, just pi upon 4, right? That's what this thing is. Yes. So it just means b equal to a square. That's our first equation. What else do you have? At pi upon 2, these two should be equal. It just means b is equal to 0, right? That's equal to what? So like sine of pi upon 2 is just 1, cosine of 2x, cosine of pi, right? Okay, just 2b plus a cos negative 1. Yes. Which means a equal to negative b. Okay, but we already know that b equal to a squared. Wait, what? That means, hey, how does that even work? Okay, a must be negative in that case. That was very weird. Right, so like b equal to negative a. This means negative a is equal to a square. Means either a is 0 or it's negative 1, which correspondingly has b equal to 0 or 1. So there are two such ordered pairs, right? Yeah, I mean, like you could just have a equal to 0, b equal to 0. Then this is like x, then this is the square root of 2x cosine. Yeah, yeah. Yeah, the condition is satisfied, right? So number of ordered pairs, 2. Next, 8. If the function is continuous, is continuous in the interval negative infinity to 6, then the values of a and b are respectively. Okay, so at 1, what do you have? Is 2 sine of pi upon 2 is just 3. 3 is equal to, so at x equal to 1, this just becomes a plus b. And then at 2, it's 2a plus b. That is equal to, just put 2 in there. It's tan of pi upon 4, right? Just 1. It just means 2a plus b equal to 1, and then a plus b equal to 3. Subtract, just get a equal to negative 2, which means that b is equal to 5. So the values of a and b are negative 2 and 5, which is c. If x is this thing, then so it's x sine x when it's between 0 and pi upon 2, and so this is continuous, at least. It's also differentiable in this range. Then, so at pi upon 2, right? Of course, it's continuous at equal to 0 and it's differentiable at x equal to 0. Okay, what we want is, oh, okay, it's not defined for x equal to 0. That's kind of weird. Anyway, so if it's not defined for x equal to 0, how can it be continuous? Anyway, just figure out what is happening at pi upon 2. When you put pi upon 2 in there, this thing just turns out to be pi upon 2. And this thing, what does that turn out to be? Pi upon 2 cosine of pi, it's negative pi upon 2. Okay, that's not good. So, oh, that just means like it's discontinuous at that point, right? So no need to check the differentiation, right? That's the thing. It's discontinuous. Next, 10th. Okay, this function is continuous like equal to 0, then the value of a will be, it's a at x equal to 0. You put oh, it's like one is fine. So just 2 sine square of 3x, right? So it's just like approximately it's 2 times of 3x squared, I think, upon 3x squared. So this is what, 2 times of 9 upon 3, which is 6. So a should be 6, right? Okay, and what about this guy? So when x is bigger than 0, it's this thing. Okay, square root of x upon square root of 9 plus, okay, this is completely one radical. Okay, cool. Square root of x. So rationalize this thing. That's what they call it, at least. This will just be square root of x. And then you will have to actually multiply by this thing to get the thing done, right? So square root of 9 plus square root of x plus square root of 3. Oh, okay, plus 3. Yeah. So that, like, on the top and bottom, so that you just get square root of x in the denominator and then this thing in the numerator. This cancels, which is this thing. As x tends to 0, this thing tends to 3 plus 3 is 6, which means a equal to 6 is the value. Next question, so that it's continuous. Okay, number of points of discontinuity of g of x. Seriously, I mean, oh, okay, it's not g of x, it's g composed with f, and that applied on x. Wow. That extra space that could have really, okay, fine. So this is g of f of x actually, where f is this and g is this. Okay, that's not good. So the wholes are also discontinued points, right? So of course x equal to 1, that works. That's a point of discontinuity. Otherwise, this isn't that the same as the last. Oh yeah, this is this example they also had in chapter exercise. Yeah, in chapter exercise as well, they had this example or something like that. Well, yeah. So at x equal to -3. Oh, I should say g plus. Yeah. Wait, no, we are doing g of f. Oh, sorry. That was really wrong. So f is just this thing, which means that of course -3 and 2 are points where it's discontinuous, but not defined. And g is this. Okay, so g of f, that will be like 1 upon f minus 1. So this, it's discontinuous when f is equal to 1. Otherwise it's like defined and everything, and because this is kind of a rational function, it will be continuous wherever it's not going into these asymptotes, right? The only problem is just asymptotes and holes. Otherwise there's no breaks. Okay, yeah. So x equal to -3 2, that works. And when f is equal to 1, which means x square plus x minus 6 equal to 1, which like x square plus x minus 7 equal to 1, right? This will have two solutions because the discriminant is just positive. So those 2 points will also be problematic because that's like asymptotic points. And these are the whole points, if that makes sense. Yeah, right. So there are like 4 points where it's discontinuous. This definitely does not have -3 and 2 as solutions. Yes, it doesn't. How could it? Rational root theorem, right? Okay, that just means C is the answer. Next question. Come on. 12th. 12th is this function not defined at x equal to 0. The value which should be assigned at x equal to 0 so that it is continuous is, okay. Uh, what is natural log of b? Natural log of a plus x minus a. Interesting. Very interesting. Natural log of a plus x, huh? Oh, I think I know what they are trying to do. So it's like natural log of b. I'm just gonna do the first one first. So that times of natural log of a times 1 plus x upon a. Yeah. This can be split as natural log of a plus natural log of 1 plus x upon a. Then this times natural log of b is just natural log of a natural log of b plus natural log of b times natural log of 1 plus x upon a. Now, in the difference, this will actually cancel because it's, yeah, it has a similar term over there. That will cancel. And okay, here's a negative thing, but whatever, it doesn't matter. And then this thing, um, yeah, well, God. This can be approximated as just x upon a, I think. And this is a natural log of a, right? Similarly, for the other one, it's natural log of a, natural log of b, and the natural log of a times, uh-oh, this should have been natural log of b. Wait, no, something's not right about this thing. It should have been natural log of b. Sorry for that. This is the thing. Okay. Then you got negative, and then in that case, natural log of a times natural log of 1 minus x upon b, right? Yeah, which is approximately like negative x upon b. So this will just be what? Plus x upon b times natural log of a. Cool, and all of that upon 2x, right? So what we are doing is just natural log of b upon a plus natural log of a upon b and all of that upon 2, which is like natural log of b power 1 upon a and a power 1 upon b, then half of that or something. Oh, okay, they don't want it like that, huh? Fine, they want it in a different way. So this will be like natural log of a power a b power b upon 2ab, right? Yeah, which is b. Next question. 13th. Is it just me or these are much simpler than what I thought? Okay, f is this thing then. So when x is not equal to 2 is this thing, of course, just do this x minus 2 and then you got x minus 3. This is x minus 2 times x plus 2, right? So as x approaches 2, this thing just becomes what? Negative 1 upon 4. And when x is equal to 2, it's 2. So limit as x tends to 2 plus, yeah, it's 1 upon 4. As it tends to 2 minus, it's 1 upon 4. As it tends to 2, yes, it is negative 1 upon 4. Wait, negative 1, oh, come on. This is not correct. A is not correct, and D is not correct. Because it should be negative 1 upon 4, right? Yeah. B is correct, and it's not continuous at x equal to 2. So B is the answer. Next question. Because, you know, the limits are equal. I mean, limit exists basically, but the function is defined at some different value at that point. Okay, next, 14th. F is this thing then. So what do you want? X tends to 0. All right. So this thing is negative 1. So like x tends to 0 minus it should be just negative 1. Yeah. When it tends to 0 plus, it should be 0. So both these things are wrong. And of course, it's discontinuous because these two don't work. So C. 15th. F is this thing, then the value of A and B, if F is continuous at x equal to 0 are respectively. So it's this thing, that thing, and that thing. Fine, at x equal to 0, right? So it's like 1 plus 0 to the power of A. Okay, that's what's going on. Huh? Right. So yeah, just e power A upon 3. Obvious things like e power A upon 3, that is equal to B is equal to so just e power 2, I think, which means A equal to 6 and B equal to E squared. 6 comma E squared. That's the A and B values. So that's option B. Next question. And yeah, then 10 of 6x upon 10 of 3x is just 2 approximately, right? For small x values. Okay, next question. And we just wanted x to 0. So the limiting case is gonna work out. 16. F of x be defined for all x bigger than 0 and continuous. Let f satisfy f of 4x upon y is equal to this. Okay, fine. Okay, it's defined and it's also continuous. F satisfies this equation for all x and y, and f of 4e is equal to 1. Then, oh god, right, it's like 4x upon y is equal to f of x minus f of y. Oh god, okay, it's bounded. It's that's just weird, isn't it? Huh. You could always differentiate with respect to x on both sides, so we'll just get this thing. F dash of 4x upon y is equal to f dash of x minus, well, that's constant, so that just goes away. Sure. Yeah. So that's when you differentiate with respect to x, right? Okay. Awesome. Now what? So like this is going to be true for all values of x and y. Okay. Wait, okay, they never said it's differentiable. Oh, they only said it's continuous. There might be jumps in its differentiability. Huh. Uh, it's defined, it's continuous. Other than that, they didn't actually give us anything. Oh, they did give us that f of 4e is 1. Huh. Okay, we don't have time to prove that it's differentiable or not differentiable or whatever. I'm just gonna assume it is, right? And then let's see what happens. So since this happens, yeah, like what can we do in that case? Hey, you know what? What if say we differentiate with respect to y instead, right? Yeah. Let me just give what negative 1 upon y squared f of, oh sorry, it should not be this thing. Oh wait, just sorry. When we differentiate it with x, it's f dash of this thing, but then the inside stuff should come out. So it's like 4 upon y and then all of that. Right. We should have done that. Huh. Now what? Like f dash of x is equal to f dash of 4x times 4, it seems. It's not helping. Not like x upon y or something. I don't want that 1 upon y stuff. We just say 1 upon y is equal to u. So it's this thing, f of u, and then f dash of 4xu is equal to f dash of x. And this works for all kinds of things, right? Oh, if that's the case, then right, just put u is equal to, okay, that won't help. I thought you could put u equal to something like, it just won't help, right? It won't help. Oh, but we could put x is equal to 1 in this thing, right? Yeah. So it will just be 4u f dash of, or let's say x equal to 1 upon 4. That would work. So this will just be u, and that's equal to f dash of 1 upon 4. So we don't know what this thing is, but we'll figure out. So then what do you have? Okay, it's like dy upon that. And okay. So df of u, just gonna say it's df. So df is equal to f dash of 1 upon 4 upon 4. And then you got 1 upon u and then du. So du upon u or something like that. F is equal to f dash of 1 upon 4 upon 4. And then you got natural log of u plus some kind of constant, of course. Right? So all in all, what you are saying is f is of the form a e power ax, right? Where these are just real numbers. Cool. So let's put that in this and let's see what happens. So wow, this is really bad, isn't it? Oh, sorry, it's not of this form. It would be of this form if natural log was over here. Sorry for that. So okay, this is the thing. F can be written like this. Okay, awesome. So what you're seeing is f is of this form: a natural log of x plus b. Now let's put that in this thing and let's see what happens. So a natural log of 4x upon y, okay, plus b is equal to a natural log of x upon y. Okay, that's very weird, which means that a natural log of 4 plus b is equal to, so it's like b is just equal to negative a natural log of 4, right? Just put that in there. It's like f is just equal to a natural log of x upon 4. That makes sense. Sure. Yeah, that looks good. So just now that works out. Okay. Yes, it does work out. So that's awesome. And what else do we know? F of 4 a equal to 1. Just put that in there. It's like, yeah, just a equal to 1. So f is just natural log of x upon 4. Right. So a is wrong because we already got function. So we can say it's wrong because we already have function, right? F is bounded. So as x tends to infinity, this thing tends to infinity as well. And so like the function is actually like this thing. So it's going very negative and then it's very positive. No, it's not bounded. It's not bounded because it can go very positive as well as very negative. So no. Oh, and of course it's like defined for x bigger than 0 only. Huh, interesting. Anyway, what else do we have? Um, limit as x tends to 0 of f of 1 upon x is equal to 0. So f of 1 upon x is just natural log of 1 upon 4x because 1 upon x, right? So yeah. So the limit as x tends to, and this can be written as negative natural log of 4x basically. We are saying as x tends to 0 of the, oh, that doesn't make any sense because it's going to be plus minus infinity. Actually, negative infinity for sure. So it's not 0. It is just infinite. Yeah. Limit as x tends to, what is this thing? 4 of x f of x. So like x natural log of x upon 4 as x tends to 4 is just 4 natural log of 1. That's 0. So yes, D is correct at least. Next question. 17th. The main problem that I have with these kind of equations is that they always assume nice functions without being told that we have to assume nice functions, right? So for this example, we had to assume it was differentiable at everywhere except x equal to 0, of course. If we didn't assume that, we would maybe have got some other kind of function. Who knows, right? 17th. F of x is equal to mod of x plus 1 sine of pi upon mod of x plus 2, where this denotes the greatest integer function. Points of discontinuity of f of x in the domain are... Oh, yeah. So whenever this thing is 0, that point is just not defined. So yeah. And otherwise it is defined, but okay, we want discontinuity. Even if it's defined, it could still be discontinuous, right? Okay. And the domain only. What is the domain? Like, okay, integers want to work for x, sure. Other than that, what is the problem? Huh. It's kind of a weird thing. Yeah, other than that, what is the problem? All kind of real numbers would work, right? Except integers, of course. Oh, okay. So if that's the case, integers are not in the domain, then that means, right, those are not points of discontinuity anymore. Okay. Wait, they are using integers even now, but we already said that those cannot be in the domain. Then how are they using this? Huh? Oh, okay. Maybe what's happening is that x plus 1. Oh, yeah. Okay, that explains everything. Sure. But you already know the integer. Not all integers, just... sorry. That should have happened. What am I doing? Seriously. So wherever the floor of x plus 2 is 0, that is not in the domain. That's the only restriction. Right. When does that happen? That happens when x plus 2 is greater than or equal to 0, less than 1, which means x belongs to -2 to -1. So this, right. Other than that, everything is in the domain. Okay. So where will it be discontinuous? Forcing to switch n. That's going to be happening. Sure. So let's just check the options. Integers. Do all integers behave that way? So whenever this is an integer, let's just say x is equal to n, then this is just n plus 1, and then you got sine of pi upon n plus 2. Okay. This is really a weird thing, actually. Some other way. Come on, think about it. Isn't there some other way that I can do this? What about this kind of function? X minus 1 sine of pi upon x. Think about this function for a second. Think about this guy's derivative. It will be sine of pi upon x. And this guy's like this plus x minus 1 times pi cosine of pi upon x. Right? Yeah. So all in all, for big enough x values, this thing will actually be like this derivative is positive, which means that as you increase your n value, yeah, your function actually increases, right? Yeah. And what else? So like for very negative x values, so large negative x values, this thing is approaching 0, so like this doesn't really matter. The major stuff comes from here, right? So cosine of, that's what happens when x becomes more than pi upon 4. Oh, sorry, more than 4 in magnitude, but in the negative side, right? That's when this will happen. So in the negative side, it will start to become what? Like, okay, it will become negative, right? This thing will just become negative, which means what am I doing? It's going to decrease. Sure. So the function is like this. It's going to decrease from the negative side. Some stuff happens over here, then it's going to increase, right? Yeah. Sure. Which means that throughout its increasing portion, yeah, like you just have these discontinuities because you're changing from one integer to some other integer. So the integer points are where you have discontinuities. So that's explaining why you have these things over here. Now, what points are there where it's actually not changing? Yeah, or maybe if even it's like it's changing, but it's not really. Uh, okay, I mean the integer changed, but not the value of this function. There could be points like that as well, right? Yes. So let's check the options. Does -1 work? Okay, so just after -1, you will have -1 plus h, just like the float function of h, which is 0. Okay, that doesn't work out because it's not in the domain, right? Our domain was what? Where did it go? -2 to the -1, right? Okay. Okay, this was not in the domain, sorry. So like just after -1, -1 plus h, floor function of that is 0, and then this will just be -1 plus, oh yeah, it's like 1 plus h, right? So this is still valid, it's going to be 0. So right after -1, it's 0, cool. But is that a point of discontinuity? Maybe, because the domain is not like allowing it to go any further. So you could say it's a point of discontinuity. What about -2? Okay, these are getting, this is really weird. What about 0? Is 0 a point where something bad happens? So just after 0, this is like, okay, this thing will be gone. It's like just 0, right? Oh yeah, okay, that is 0, okay. And just before 0, this is like 1 plus, okay, no. Just before 0, this is like 1 plus something, sine of pi. That's 0 as well. Oh, that somehow worked out. So that means just before 0 and just after 0, your function has the same value, which is 0, both the times. Which means that b should be the thing, right? Yeah. And of course, at -1, it is in fact discontinuous because it's not in the, like, it's not defined on the left side, and then similarly for -2, it's not defined in the right side. So how do you even make sense of that? Which means I think B is the answer. Next question, 18th. 18th, if the function is continuous at each point of its domain, then the value of f of 0 is. This function is continuous at each point of its domain. Okay, fine. So 2x minus sine inverse of x upon 2x plus. So its domain is really just -1 to 1, right? Yeah, inclusive, of course. So what is value of f of 0? Oh, that's what you want to find. Seriously, why did you make me think about the whole domain in that case? Right, so as x approaches 0, this thing just becomes like 2x minus x upon 2x plus x approximately. So yeah, just 1 upon 3, which is B. Next question. Next is 19th. The value of a and b such that this function is continuous everywhere are. Okay, yeah, these three functions are actually continuous by themselves, but then they're changing. So negative pi upon 2, negative pi upon 2 changes. It just negative a is equal to negative, oh, it's -4, sorry. Is equal to negative a, negative b, right? And at pi upon 2, it will be a minus b is equal to 0, right? So a equal to b, which means that a is just 2. So like, yeah, a equal to b equal to 2. That looks good. So yeah, which of these options? C. Next question. 20. 20 is if f is this thing and f is continuous at x equal to 5, then f of 5 is. So it's like x minus 5 squared upon, what is this, x squared minus 7x plus 10, x minus 5 times x minus 2. Yeah, it cancels, whatever. This is f, okay, x is not equal to 5. Okay, and f is continuous at x equal to 5. At x equal to 5, it's going to approach 0, right? So f of 5 should be 0. Next question. 21. 21 is in order that the function is continuous at x equal to 0, then it's x plus 1, and then you got, so at x equal to 0, right? Okay, cool. It's 1 plus x to the power of 1 upon x to the power of x cot x, like x upon 10x basically. As x tends to 0, this tends to e, and this tends to 1, so yeah. f of 0 should be defined as e, which is c. Okay, next question. 22. 22 is the function f x is equal to sine of mod of x is continuous everywhere. It's not differentiable at all points. I don't think it is. Is it? Okay, let's try it out. So at x bigger than 0, just like sine of x, right? So the derivative is just cosine of x. And then otherwise, it's like sine of negative x. The derivative will just be, negative cosine of x. So at x equal to 0, these things become 1 and negative 1. So of course, it's not differentiable at every point. It is continuous though. So it's continuous for, and if I actually try to graph this, maybe just like this and then just copy it or reflect it. Yeah, that's what it's gonna look like, which means it's not differentiable, but it is continuous. So A looks good and continuous for only certain points. No, it's continuous for all x. Next question, 23. If f is this thing, it continues at x equal to pi upon 3, value of lambda is. When x is not equal to pi upon this thing, okay, let's pi upon just lambda. Fine. Wait, but we don't care about that. We just care about, oh, it's continuous at pi upon 3, right? Huh. That falls into this category. So just put that in there. Okay, let's just say x is equal to pi upon 3 plus h, right? Then this will just become what? Pi minus 3x is just minus 3h. And what is this thing? I'm gonna sine of 3x upon 2. It's like 1 minus sine of 3 times of this thing, which is pi. Oh, actually 3 upon 2. Fine, just pi upon 2 in that case, right? Then you got plus 3h upon 2. And this thing just turns out to be what? Cosine of 3h upon 2 is just 1 minus cosine of 3h upon 2 upon negative 3h. It should be 2 over there, which is like 2 sine square of 3h upon 4 upon negative 3h, right? So this is you know what? Wait, it's why is it a square? Something's not right about this. Wait a second. Oh, it's gonna be 0. I guess it's going to be 0 because there's no square in the denominator, so it's just 0. Huh. Lambda. Wait. Wait. What? We don't care about what it should be. What? Huh? I think this must have been when x is not equal to pi upon 3 and x is not and x is equal to pi upon 3 and not pi upon 2, because otherwise this question makes no sense. We don't care about lambda, right? We only care about the continued x equal to pi upon 3. There's a typo in there, right? So, oh, fine. The lambda must be 0 if it is actually pi upon 3 over here. Then C is the thing, I guess. Next question. Because on the numerator you get like lambda square and numerator you just get lambda. Sorry, you get x square and then you just get h. So that's why. 24th. F is this thing, continuous at x equal to 0, then f of 0 equals. Oh, yeah, whatever. Rationalize this thing. So 4 minus x is just negative x upon 2 plus square root of x plus 4. You got sine of 2x. X equal to 0, right? Approximately 2x is just negative 1 upon 2 times of this stuff, which is 2 plus 2, which is 4. So negative 1 upon 8 is the f of 0 value. Right. 24th C. Oh, it's negative, so it's D in that case. Next. 25th. If this function is what? Wow, that's bad. So it's continuous at an infinite number of points because like it's different functions, right? If x is rational, it's this thing, and it's yeah, it's at infinite number of points. It's discontinuous. It's 26. Yes, sorry, 26, not 36. This function will be defined by x squared plus e power what is this thing? 1 upon 2 minus x power of negative 1. Okay, continuous from right at point x equal to 2. Huh? What? It doesn't matter. I mean, you can also define it to the left in the similar fashion, right? So it doesn't really matter. So, oh no, it does. It does. Okay, so when it says it's continuous from right at the point x is equal to 2, yeah, it actually does matter. So what is the thing? X is just 2 plus h, where h is a positive number. That should be the thing. Just put that in there. We'll see what happens. So this is just 2 plus h squared, approximately 4 plus this thing. So it's e power 1 upon 2, let's just negative h. So negative 1 upon h approaches what? Infinity. Sorry, negative infinity. It's e power negative infinity on the power of negative 1. This thing is approaching 0. So it's just 4 power negative 1. Yeah, yeah. So just 1 upon 4 is the thing, right? Yeah, B is the answer. You don't actually have to do any kind of limits. It already just gave us the answer. Fine. 27. This function is not defined at x equal to pi. The value of f of pi, so that f of x is continuous at x equal to what? Oh, okay, okay, fine, fine, fine. So just put x is equal to pi plus h, right? This will just become what? 1 plus cosine of h minus sine of h upon uh, like 1 plus cosine of h or so. Why don't you just put pi in there? Is something wrong? Oh, yeah, something is wrong, in fact, because that's not okay. Fine, fine, fine. Just keep going. It should be negative actually over here, right? Yeah. And then plus sine of h. That's good. And then just use Taylor expansion. So this will be like h square upon 2. This is plus h over there. This doesn't actually matter in front of this thing. Okay. 1 plus cosine of h is like 1, and then you got plus 1 minus h square upon. That is plus, right? Or what? So as okay, when you put pi over there, just 1 minus 1. What? Wait, something's not right. It should be negative 1 over there. Sine of pi should be 0. Oh, okay. I get what went wrong. Seriously. It should be just 1 plus sine of h. Because when it's pi, it's not changing. So sine to cosine, that's not a change. And then you got minus cosine of h upon 1 minus sine of h minus cosine of h. So then 1 minus cosine of h is approximately just h square upon 2. And then this is plus h upon h square upon 2 minus h. It approaches just negative 1, right? So this should be negative 1. Yeah. Next question. 28. Oh, and in the case you don't know what a Taylor expansion is, you should watch that video in my calculus playlist. That explains it the best I can. Okay, 28. Or you can just watch some other video which explains it better. Okay, if f is this thing, is continuous at x equal to 0, then k is. Okay, at x equal to 0. Well, this thing approaches what? 3. So, what is k though? Where is k? Oh, okay, here is k. Fine. So this should be 3. Okay. And just rationalize this thing. So that cancels. It's just 2kx upon x, and then you have this thing square root of 4 plus. Yeah, so kx is approximately 0. So it just means 2 and then plus 2. So just 4 over there, right? Yeah. Yeah, of course. Which means it's like kx upon 2x. So k upon 2 is the value of its limit. That's equal to what? 3. So k equal to 6. Next question. 29. 29 is the function f is equal to mod x plus mod x upon x is. So seriously, that's just horrible. So this is continuous at the origin. It's not, because it contains 1 upon x, which, yeah, that's a problematic thing. Okay, this continues at the origin because mod x is no. Yeah, because this thing is discontinuous there. Okay, that's just wrong. So C should be the thing. I mean, think about it. Both the signum function and whatever this thing, I mean, okay, that actually is not defined, because to define the signum function, you use this when x is not equal to 0 and 0. you stated that it's 0 when x is equal to 0, right? Because if you try to put x equal to 0 in this thing, it will give you not defined. So you can't, right? 30. Differentiability. Okay. Consider f is equal to this thing. What about it? X e power x minus 1. Okay. Discontinuous everywhere, continuous but not differentiable. Okay, at x equal to 0, this just approaches what? It's like, this is just, oh god, it's x upon mod of tan x, huh? The e power x minus 1, that is approximately x. Okay, it's like this then. So x squared upon mod of x if you want. Signum function of x times x. So yeah, it's going to be 0 in both cases. Okay, fine. What that means is, yeah, like this thing is actually continuous at x equal to 0. Very weird, but that somehow happens. And it's discontinuous everywhere. But it's not this. No, it's not discontinuous everywhere. It is continuous but not differentiable at x equal to 0. It's differentiable everywhere, negative 1 to 1. Right, just figure out what it is at 0. We'll see what happens. So when x bigger than 0, or this is x between 0 and pi upon 2, something like that, this just becomes what? X upon tan of x, and then you got e power x minus 1, right? So the derivative of this guy, that will just be, so you got one, yeah, just natural log of that, and then you get the thing, right? Don't you? Okay, then plus 1 upon, okay, just e power x upon e power x minus 1, I guess. Natural log of tan of x, but it's negative, of course. So negative, and you got tan of x over here, and then this is secant square of x. Looks good. Yeah, so this is, what was this once again? Oh yeah, we actually have to put x equal to 0 in there, right? So this thing we saw just approaches 0. Oh yeah. This approach, okay. Still there's some stuff to be done. This approaches 0 as well. Right, just put that inside and we'll see what happens. Just e power x minus 1 upon tan x first of all. That's the first part. Then you have e power x just approaches 1 in any case. It's just x upon tan x. That's the next part. You know what, like, okay, x upon tan x is 1 approximately in any case. So just e power x minus 1. Yeah, just approximate. Just approximate everywhere. This will be x squared upon x, which is just x. This will be 1 upon x plus just 1 upon x minus secant square x is 1 tan x x cancels 1. It's approaching 1. Yeah, that's good. So the right hand limit is just 1. What about the left hand limit? For the left hand, oh no. Okay, so for the left hand limit, this will just be negative of whatever it was, right? Yeah, yeah. That's just bad. I mean, everything still works out the same way, sure. Right, okay. Yes, it's just not differentiable because at that point it becomes negative 1, right? So it's continuous but not differentiable and x equal to 0. So it's B. Next question, 31. Function f is defined by x upon 1 plus mod of x, and f is, what is this? Differentiable, okay. Everywhere in its domain. What is the domain of this thing? All real numbers, of course. So it's differentiable everywhere. Okay, when x is bigger than 0, it's just x upon 1 plus x, which can be written as like plus 1 minus 1, just becomes 1 minus 1 upon 1 plus x. So basically 1 plus 1 upon 1 plus x squared. Since x is bigger than 0, this thing is like defined and everything. When x tends to 0, this basically becomes what? 1 plus 1, 2. When x is less than 0, you just have x upon 1 minus x, right? Yeah, which can be thought of as negative 1 plus 1 upon minus x. And the derivative of this thing would just be what? It's like negative. That negative was cancelled. Okay, this still cancels out like 1 minus x squared. Interesting. Oh, this should not have been, okay, this 1 was not supposed to be there, just equal to 1, right? At x equal to 0, it just becomes this thing. At x equal to 0, this becomes 1 as well. So, wow. That was something. Uh, yeah. I guess I know why that happened actually. Fine, but the main thing is that it just becomes equal. So this is differentiable at x equal to 0 as well, and then otherwise it is, in fact it just is differentiable everywhere, so no need to worry. X equal to plus minus 1, I don't think you have to worry about that, because yeah, you don't have to. So yes, it's differentiable everywhere in its domain. So to the next question, 32. uh, the value of the derivative of f of x is equal to mod of x minus 1 plus mod of x minus 3 at x equal to 2 is, sorry, what the value of the derivative of this function at x equal to 2, when x is equal to 2, like, okay, x minus 1, so when it's near to x minus 1 will just be x minus 1, and x minus 3, the mod of that will be 3 minus x actually. That just means what, 2, yeah, that's what it will be. So between 1 and 3, this is just 2 throughout, so the derivative is 0 at that point. There we go, here's the answer. Next question, 33. The function f defined by this, okay, is of x squared. Wow, that's interesting. So it's 0, right? The limit is 0. So yeah, okay. What about the derivative though? So check the derivative first of all. It's like 2x cosine of x squared upon x minus sine of x squared upon x squared. So as x tends to 0, this just tends to 2, and this tends to what, 1. So it's 1 on both sides, right? Yeah, that looks cool. So it would be differentiable. Okay, it is, in fact it is differentiable. What am I talking about? It is continuous, of course, because this approaches 0, and it's also differentiable because clearly it is, right? Yeah. So continuous and derivable at x equal to 0. Cool. Next question, 34. 34 is, if f is equal to mod of ln of mod of x, then f is continuous and differentiable for all x in its domain. The domain of x is just all real numbers, right? Except 0, of course, because then it's just bad. Uh, wow, mod. Okay, interesting. Okay, let's see what happens. So, wait. It's not continue. How can it might be continuous? Fine. Uh, oh, seriously, can't believe. At x equal to 0, there's a bit of a problem because it's like going to infinity, and I'm not sure what to think about it. Should it go to infinity or not? Uh, I mean, okay, maybe like 0 is not in its domain in the first place, so we don't have to worry about that. Right. Then, in that case, just make 4 sections for this thing. So first, we'll just think about, okay, it's like 1, 1, might have 0 over there. Okay, it's maybe 1, sorry. So in this region, your mod of x is just the same thing as x, right? Okay, it's kind of interesting. Yeah, and okay, so that's just the same thing as x, and the mod of that thing, okay, it's just positive or negative, it's positive, right? So it's just equal to natural log of mod of x. Over here, it's just equal to negative natural log of mod of x. You know what? Okay, just extend this throughout. Like, it's just negative natural log of mod of x in this region, and in these two regions, it's natural log of mod of x. So the derivative of natural log of mod of x, what would that be? When x is bigger than 0, no doubt it's just 1 upon x. And x is less than 0, what you can do is just put x is equal to negative y. So just have natural log of y, and then you want d upon d negative x, right? Oh, sorry, d upon d negative y. So it's just negative d upon dy of this thing. which just turns out to be 1 upon y, but then negative of that. So it's, yeah, just 1 upon x. That makes sense? Which means that the derivative of natural log of mod of x is 1 upon x throughout. Cool. Yeah, I mean, that's the thing. So uh, in this region, the derivative is just 1 upon x. In this region, the derivative is once again just 1 upon x. Yeah, even though x is actually negative and whatever. In this region though, it's negative 1 upon x. Cool. So when x is equal to 1, right, what happens? I mean, this just becomes negative 1, this becomes 1, this becomes 1. Sorry, this can't become anything because just talking about this point, right? So it becomes negative 1, this becomes 1. So at 1, it's discontinuous. So the derivative is discontinuous. So it's non-differentiable. Similarly, for negative 1, it will be non-differentiable, which means it's continuous everywhere, but it's not differentiable at x equal to plus minus 1, which is B. Next question. 35th. The left-hand derivative of the function mod of what gif of x sine of pi x at x is equal to k and integer. Okay. X is left-hand derivative. Just the left-hand derivative and not the right-hand one. Oh, that's weird. Wait, something's not right about this. Okay, there's fine. Like it's gonna approach k or something. K is still less than or equal to x, right? We talk about left-hand derivative. Yeah, okay. It actually means the left-hand limit of the derivative, right? Yeah. It doesn't mean that you take the actual value at that point and then do the derivative by using its definition. No. I think you really just want the derivative on the left hand side. What's that? Yeah, I guess so. Just figure that out in that case. So what we're doing is x is equal to k, which is an integer, minus, let's just say h. Okay, I'll just use something else, minus u, where u is a fraction. So this just becomes what? K minus 1, that's this part, and then sine of pi x. So sine of pi times all of that, like sine of pi k, that is k single pi negative 2 pi point. So that's just negative 1 power k. Yeah, that makes sense. So just negative 1 power k, and then sine of like negative what? Negative u, right? Sure. Wow, this is just seriously bad. How about we do this, right? Where u is, even though it's like a negative number, but at least now the dx and du things are actually the same, right? So just do sine of u in that case, although it's negative, right? Or you could always just do this thing, right? You can say it's k minus 1 plus u. That's gonna make sense, sure. So wait a second. That's giving a different answer than that one. So what went wrong? K plus u. Yeah, like u was negative, isn't it? Hmm. I mean, you just want d upon dx, but then that's the same thing as d upon du. But oh, you will have to evaluate the thing, right? But then these are just constants, so why do you want to worry about it? Just use this definition. It's the simplest thing that you can do, right? So it's just this thing: k minus 1, negative 1 power k minus 1 sine of u, right? Where u is just a positive number, and then you want d upon dx of this thing, right? Which is the same thing as d upon du, because both, like, they are just linearly related. And okay, I don't have to explain that. Fine. So you want the derivative, just x minus, sorry, k minus 1, and then you got negative 1 power k minus 1. Then you got cosine of u, right? Cool. Usually I'll just do du, but then du is the same thing as dx. So yeah, this looks cool. And then cosine of u, you want the derivatives. Like, okay, u is approaching 1. Oh, okay, you should have done that. And wait, it's pi. It's pi over there. It's like pi x. Then this will be pi u. And then you also have this pi. And u is approaching what? 1. Right, that's where the thing would manage itself. So since u is approaching 1, this will just become negative 1. Over there, u was approaching 0, so this will just become 1, right? And it will still manage out. So this is just negative 1. What does that mean? Um, Pi k minus 1, negative 1 power k, that's the thing, right? Yeah, so it's A. Next question. That's the left hand limit of the derivative. 36. The function, this function is continuous at not differentiable. It's mod x plus mod of x minus 1, huh? So at x equal to 1, let's just figure out. So when it's 1 plus, this is just x plus, okay, like it's already there. So it's like, let's just say x equal to 1 plus h, then just fed up. 1 plus u, right? That's gonna work out. It's just 1 plus u, and then what am I even doing? Why do I even care about it? We just have to think about the derivative because we already know it's supposed to be continuous. So then it's just x plus x minus 1 on one side, right? The more than one side, and then x plus 1 minus x on the less than one side. So this just becomes like over here the derivative is just 0, over here it's 2. So this is not differentiable at x equal to 1, neither is it differentiable at x equal to 0 because it's the x and then negative x, right? Yeah, so it's not differentiable at 1 or 0, but it's continuous everywhere. Is continuous at x equals to 0? No. Continuous and differentiable? No. A is the answer. Next, 37. 37 is let f be this thing, then the function is continuous everywhere, right? Okay. Differentiable, not so much. Not differentiable at x equal to plus minus 1. Yeah, that makes sense. Because it changes its definitions, right? And then the slope changes by a factor of 2. Okay, a term of 2, right? So it's continuous everywhere, but not differentiable at x equal to plus minus 1. At 0, it is, in fact. So B is the answer. 38. The derivative of the function, okay, what? Is everywhere, okay, fine. It's continuous everywhere and differentiable at x equal to negative 1. Then A comma B is. So fine, okay, I'm seeing what's going on, and it's differentiable at wait, the derivative is different. Okay, okay, that makes sense, right? Okay, well, first of all, okay, wait, the derivative is it's kind of a weird thing. This everywhere continuous, and first of all, this function by itself should be continuous, right? Only then can you even talk about derivatives, I guess, right? So okay, let's just right. First of all, what I will do is just take up the second derivative, right, of this function because that must be continuous as well at x equal to negative 1. So what do you get? You just get a equal to b. Yeah. So that just means like this is just ax squared plus ax plus 2 and this is ax squared plus ax plus 4. Okay, this doesn't make sense because how can that be uh oh, that's bad. Oof, doesn't make any sense. The derivative is continuous everywhere and differentiable. What is this? Like this is a twice differentiable function. That's what you're saying, isn't it? But if that has to happen, then a equal to b, and that would mean that these are not the same functions. That would just mean it's oh god. then it's not continuous in the first place. So it's not doable. None of these. There's no such A and B that this is going to happen. 30 is just weird. Either it's not conveying what it has to, or something's wrong about this. Next, let f be a twice differentiable function. Oh, this was in fact actually a twice differentiable function. But then, like, how could you have this guy's second derivative? It should be this the same, right? Like the limits should be the same at x equal to -1, but then the second derivative will just be like what? 2a and 2b, and those must be the same, which means a equal to b. That's the only way. But none of these options have equal to b, and if a equal to b, then it's having a difference of 2 at x equal to -1, right? That's a jump discontinuity, which makes no sense because it's already a twice differentiable function. So there's no such a-b pair that this happens. Okay, 39. F be a twice differentiable function such that g dash of x is equal to -f upon g times f dash, and that's equal to g upon f times h, which is equal to this. What? Okay. If h of 5 is equal to e power 6, then h of 10 is equal to. Think, what can we do? So this is a, oh, it's not times f dash, it's actually a comma over there. Huh. Oh, and h of x is this thing. Wait, why did they even tell us about h? Oh, it involves f and g, that's why. Fine. So first of all, we have this and that, these two equations. So we just have g dash is equal to -f upon g, and f dash is equal to g upon f, right? Exactly. So like g dash g is equal to -f, and oh, interesting. It's like dg upon dx, right? Okay, well, dg upon dx upon df upon dx, you could use that thing, I guess. So what I'm thinking is just, divide these two equations. So you just have dg upon dx upon df upon dx. Isn't that like dg upon df basically? That's equal to what? So when you divide, you just get like -f square upon g square. I guess that makes sense, right? It just means like g cube. Sorry, yeah, g. That is the thing actually. G cube plus f cube is kind of a constant. That's what it means, right? We just have to figure out what that constant is. So really just h is equal to e power some kind of constant plus x. This is like basically a e power x, right? Okay. And if h of 5 is equal to e power 6, so it should just be e power 5, but then it's e power 6. Actually, the constant is just 1. So h is equal to e power 1 plus x. That's what you're saying. So h of 10, what will that be? Yeah. Wait, do we even need? Okay, fine. Whatever. So h of what? 10? Well, yeah. Add another e power 5 in there. So it should just be e power 11. So it's B, I guess. Next question. 40. The function, this function is, okay, continuous differentiable, that's one. Okay. So is this continuous at x equal to 2? Well, it is. I mean, just sine of pi, it's going to be continuous, of course. What's at x equal to 1 though? X equal to 1, this will basically become 1. Sine of pi upon 2, right? Put x equal to 1 in there, it will just be what? 2 minus 3, just -1, mod of that 1. 1 floor function of what? Uh-oh. 1 floor function of what? This is when x is bigger than or equal to 1, right? Oh, exactly at 1, you just have this. Right, even if it's 1 plus h, we don't care about it because it's just 1. Floor function is 1. So just 2x minus 3 in that 1 to 2 range, right? So that will just be -1, mod of that is 1, so 1 equal to 1. Yes, it is in fact continuous at x equal to 1. Is it differentiable or not? So like 1 plus h in that range, it will just be what? 2x minus 3, mod of that, of course. And since yes, close to 1, you have to put this thing, so it's just 3 minus 2x. So derivative will just be -2, right? For this thing, yes, at x equal to 1. And this guy's derivative, I can already see it's going to be not good. So it's just pi upon 2 cosine of, yeah, whatever. Put x equal to 1, it should just be 0. It's gone. So like, huh. Well, that was weird. So what does that mean? It's not differentiable. So C is the answer. I think we should stop now. Okay, then. Let's just check. Let's check. Come on. Wait, how long is this booklet? Oh God. Wait. Wow, this is just way too big. Right. Okay, let me go exercise 1A. First D, second C, C. Okay. Then you got DCA. Should be A. Okay. BCA. And 10th. What? Okay, BBC. 15th. Okay, BTC, BCA. 17th should be C. Wow. Then B. Okay. 19th is C. It's A. 21st, we got CAC. Then 24th, DDBCC. Seriously? Oh, that's D. Huh? 25th, it should be D. Okay. 26th, what was it? Okay, BCC. That's 29. CBA, BAB. Yes, that's the thing. 35. AAE. Okay. 38. It is D. I don't know. 39. B and then it's C. Okay. So 38. Okay, I'm not scrolling up now. That's it. So I'll end this video here. I'll see you guys in the next video. Bye.